Hello, everybody. So today we're going to talk about the oxidation of alcohols and actually talk about the specific reagents. So I wanted to start off recapping what we've talked about as it relates to the oxidation of alcohols, which has to do with how different types of alcohols, primary, secondary, or tertiary, are oxidized differently. So we saw that primary alcohols, we could potentially oxidize them to either aldehydes or carboxylic acids, and this is going to depend on the specific oxidation conditions that we're utilizing. Whereas secondary alcohols, we generate ketones through oxidation, and that's independent of the oxidation condition. The ketone is the only oxidation product that we will see for secondary alcohols. And then for tertiary alcohols, since there is no hydrogen at the carbon that bears the OH, there's no way to perform the oxidation because the oxidation requires that hydrogen to be removed in the mechanisms. And so tertiary alcohols do not undergo oxidations. Okay, so we really are going to break up our oxidation conditions into two different categories, and those are going to correspond to those that will give us aldehydes and those that will give us carboxylic acids from primary alcohols. And then, all the reagents we talk about therein, will have the same oxidation product for secondary alcohols, and we'll see that through examples. Okay, so the way that our textbook breaks this up, and I'll do the same, is they talk about oxidation in the presence of alcohols, in the presence of water. And so we're going to break it up into oxidations in the presence of water and then oxidations in the absence of water. Okay, so first we'll talk about oxidations in the presence of water. Oh, I started off that really good. Okay, so oxidations in the presence of water. Okay, so let me go ahead and write out some of these conditions. And so what we're going to see here is that these are the stronger oxidizing conditions. So we'll just put that in quotes there. So these are the conditions that are going to give us carboxylic acids from primary alcohols. So let's just show our primary alcohol through these oxidation conditions, and there's a few different ones. So I'm just going to generically write ox here, and then off to the side we'll write the specific conditions. Or at the same time, we can go ahead and look at our secondary alcohol and its oxidation under these conditions. Okay, so these are our stronger oxidizing conditions that will continue our oxidation of primary alcohols all the way to carboxylic acids, and then our secondary alcohols will end up as ketones. Okay, so we're going to end up with carboxylic acids from our primary alcohols, carboxylic acids, and then we'll end up with ketones from our secondary alcohols. Okay, so what are these oxidation conditions? Okay, so the oxidation conditions, there's generally three different ones that we can consider. Okay, so here's what they could be. So the first one is dichromate. So this could be sodium or potassium dichromate. And we run this in the presence of H2SO4, which, remember that H2SO4 really is a solution in water. So you can read this as H2SO4 plus water. So even if water isn't explicitly written, since we're running the reaction in H2SO4, which is a solution made up in water, that's where that oxidations in the presence of water comes from. Okay, so whether or not water is explicitly written, we know that it's within that sulfuric acid, and so this would fall under that category. Okay, so what did I call that? This is called dichromate. Dichromate. Okay, and again, this could be sodium or potassium dichromate. Okay, so another oxidizing conditions that would facilitate the same thing. So there's one possibility. Another possibility would be Jones's reagent, and this would be CrO3 and H2SO4. Again, H2SO4 is a solution in water. So this together, these two things together are called Jones's reagent. Okay, and then the last one has in common, what the other two does, and that's that it involves chromium. And so the last one is chromic acid. So H2CrO4, and that's chromic acid. Okay, and chromic acid again is a solution in water. So the water is present there even if we're not explicitly writing that out. When you buy chromic acid, it's a concentrated solution made up in water. So all three of these oxidation conditions would give us carboxylic acids from primary alcohols, and they would give us ketones from secondary alcohols. We're going to distinguish them away from the other oxidations we'll learn here in just a minute, as they are in the presence of water. We see that either through a solution of sulfuric acid in water or chromic acid, which would also be made up in water. Okay, so before we look at our next oxidation condition, I want to go ahead and take a look at an example or two. Okay, so our first example is here. All right, so it doesn't matter which one of these I choose. I'm going to go ahead and do dichromate in H2SO4. Okay, so first, I would probably at least make a mental note of what type of alcohols you're seeing. Okay, so what type of alcohol is that alcohol at the end? Is that primary, secondary, or tertiary? So it's primary, right? And then what about this one? That one's tertiary. So we learned that tertiary alcohols can't undergo oxidation, so we're not going to touch that one in the mechanism. But we'll go ahead and oxidize that primary alcohol all the way up to the carboxylic acid in these strong oxidation conditions. So we're not going to touch the tertiary alcohol because it cannot undergo oxidation, and we will convert the primary alcohol into that carboxylic acid. Okay, so one last example to show these oxidations. Oh, and I didn't mention up above, but I should mention it now. So we're not going to look at the mechanism of any of the oxidation reactions. So what you need to be able to do for these reactions is predict the products, okay? Or distinguish, between which type of reagents that you would need to use, whether you're going to form an aldehyde or a carboxylic acid from a primary alcohol. Okay, and then in our last example, let's look at this alcohol. And in this case, let's go ahead and use Jones's reagent. So sometimes that's written out just as Jones, sometimes it's shown with the reagents that make up that, what is called Jones's reagent. Okay, so what kind of alcohol are we oxidizing here? So hopefully you thought about that as a secondary alcohol. And I just wanted to point out here, notice how we're getting rid of a chiral center. We're going from an sp3 to an sp2 hybridized carbon. And so we're actually eliminating some complexity in terms of stereochemistry. And so again, secondary alcohols, regardless of the oxidation conditions that we're going to learn, are going to give us ketones. All right, so we've seen these stronger oxidizing conditions. So we had dichromate, Jones's reagent, and chromic acid. We're going to have one oxidizing condition, which is in the quote unquote absence of water. And let's go ahead and talk about that. Okay, so and these we'll think about as the weaker oxidation conditions. So oxidation in absence of water. Okay, and there's more than just the one that we are going to learn about, but I'm going to present to you the most frequently used one, especially as it relates to when you get to Organic 2. This is the one that your textbook and correspondingly instructor will expect you to know. But if you look in our textbook in this section, you'll see a few other oxidations in this category of in the absence of water. But I'm going to tell you about the most important one. Okay, so oxidations in the absence of water. So these are generally the quote unquote weaker oxidizing conditions. So I'll give you what the condition here is in just a second, but I wanted to write out what the products are first. Okay, so our primary alcohol is now going to give us an aldehyde. And then the secondary alcohol's oxidation product is the same whether we're using strong or weak oxidizing conditions. Okay, so our secondary alcohol is going to form a ketone. So let's label those things and then I'll give you guys the reagents. Okay, so the reagent for this is going to be this reagent that we call PCC, and it's going to be in a solution of CH2Cl2. Okay, so I'll define what PCC here is in a second. So CH2Cl2, hopefully you remember, is dichloromethane. It's our inert solvent. We learned about that way back when we were first talking about reactions. Okay, so what is PCC? So PCC equals pyridinium chlorochromate. And it has this structure. Okay, so remember I had told you, as we've kind of been working through this semester, that IUM ending tells us something. So it tells us that we have a cation. So specifically, we have the conjugate acid of pyridine. So we learned what pyridine structure was earlier, in this chapter, because we were talking about pyridine as a base that was used with thionyl chloride to convert alcohols to acid chlorides. Okay, so that is pyridinium, so it's the conjugate acid of pyridine. And then we have chlorochromate, which is this structure. Okay, and so notice we don't have any strong acid present, so there's therefore no water present. So it's this reagent, this pyridinium chlorochromate salt dissolved in our inert solvent of CH2Cl2. Okay, and so this reagent allows us to selectively oxidize primary alcohols to aldehydes. And so you need to keep track of which oxidizing conditions are going to be those that give us carboxylic acids and those that give us aldehydes. Okay, and this is the only reaction we're going to talk about that gives us aldehydes from our primary alcohols. So let's just look at an example or two of this, and then we will move on. Okay, so let's look at this molecule. And we're going to run this reaction with PCC in dichloromethane. All right, so if we were to take a look at our alcohols, we have a secondary and we have a primary alcohol. So let's assume that our reagent is in excess. And so we would oxidize both of those. We're not going to need to decide what's oxidized quicker, secondary or primary alcohols. So if you have more than one alcohol that can be oxidized, just assume that your reagents are at excess, but hopefully, we would write that just to be clear about that. Okay, so let's go ahead and predict the product. So our secondary alcohol is going to give us a ketone, where our primary alcohol is going to give us an aldehyde. Okay, and I'll go ahead and number our carbon chains so that we can make sure that we put the carbonyls at the right carbons. Okay, so carbon 1 bared the alcohol, now that's where the aldehyde is. Carbon 3 is where our dimethyl group is. And then carbon 6 is where our ketone should be. Okay, and so PCC ends up being a really important reaction as you move forward into organic 2, because notice how we're making these aldehydes and ketones. Aldehydes and ketones end up being a really important functional group for many of the reactions that you learn next semester. So this is definitely one reaction that you want to make sure that you are able to predict the products of appropriately and recall the reagents that are giving us these aldehydes from primary alcohols. Okay, so we have one last reaction that we need to talk about in this chapter, and so let's go ahead and introduce that. Okay, so our last reaction of this chapter, and then therefore of our exam 4 material, is this one. So it's called periodic acid cleavage of glycols. Okay, so cleavage, remember, means breaking a bond, and so we're going to be breaking a carbon-carbon bond, and then we need to realize what a glycol is. Okay, so a glycol is a 1,2 diol, so it's another name for a 1,2 diol. So there is a glycol. Okay, and so what we're going to do in this reaction is we're going to cleave the carbon-carbon bond of the two carbons that bear the OHs in this 1,2 diol. Okay, so 1,2 means that the two alcohols are on adjacent carbons. Okay, so the reaction is going to look like this. Okay, so we're going to have our 1,2 diol, and it doesn't matter if there's other substituents, around the carbons that bear the OHs. And the conditions are periodic acid, which is HiO4, that is periodic acid. And it turns out in this reaction, this is a similar reaction to what we got for ozonolysis, in that we're going to cleave the carbon-carbon bond, and we're going to at the same time oxidize both carbons up to the corresponding carbonyls. So in this way, we will end up with a carbonyl at both carbons that bared the alcohols in the starting material. Okay, so we could end up with a mixture of aldehydes and or ketones in our products, depending on what these R groups are. So if they're hydrogens or they're carbons, we'll either get aldehydes or ketones, or a mixture of aldehydes and ketones, just like for ozonolysis. Okay, so aldehydes and or ketones. Okay, so let's go ahead and look at an example or two of this. So first, I want to remind you that we know how to make glycols. Okay, so we have to think about first, what is the reaction that gave us these 1,2 diols? Okay, so what was the reagent that allowed me to, make these diols? So that was OSO4, so osmium tetroxide. We use that catalytically with H2O2, hydrogen peroxide as our oxidant, and then water. Okay, and so then in the next reaction, we're going to go ahead and cleave with HiO4. HiO4, and we're going to break the bond between the carbons that have the OHs, and we're going to oxidize those to the corresponding carbonyls. So at this point, we're going to have a 5-carbon chain, and then let's think about what functional group we expect at carbon 1 and carbon 5. Should we end up with an aldehyde or a ketone at those two positions? Okay, so notice how at both carbon 1 and carbon 5, there's a hydrogen present. In other words, they're secondary alcohols. And so those are going to end up giving us aldehydes, right? So if I had another carbon chain, like let's say I had a methyl group at carbon 1, then I would end up with a ketone at that position. Okay, so let's go ahead and draw our product. So we're going to have our 5-carbon chain, and then we'll have aldehydes at carbon 1 and at carbon 5. All right. So you might be thinking, well, that's funny. Why don't we just go ahead and do, ozonolysis? Why don't I just take the starting material that I, originally had and do ozonolysis? So fair point. You could do that. So, reasons practically why you would choose one of these methods over the other is the main one being the difficulty of working with ozone. So first purchasing ozone and then using it in a reaction. Sometimes it's not feasible for, research labs to use that reagent. And so you might use, the method above with, creating the syndial and then doing the periodic acid cleavage, which are a little bit more available reagents that you can purchase from quote unquote the chemistry store. Okay, so there is one stereochemical limitation that I do want to mention here, and that is that in the reactive conformation, we're not looking at the mechanism here, but if you were going to, there's a reactive conformation of the diols, and that's that the diols must be on the same face. They must be syn to one another. So for cyclic diols, they must be cis, okay? So cyclic diols must be cis. Cyclic diols must be cis to each other to undergo this reaction. So reaction, I should maybe say, with HiO4. Okay, so for linear alkanes where you have the 1,2 glycol, you don't have the same limitation because you can just rotate around the carbon-carbon bond to make the OH syn before you proceed through the reaction. But in the case of cyclic rings, remember we have this limited rotation. So like in the above example, I have limited rotation about the carbon 1,5 bond. And so if those two OHs were trans to each other, there's no way to ever make them on the same face because I can't freely rotate around that bond between carbon 1 and carbon 5. And so for that reason, you wouldn't get a reaction from the trans alcohol. So just to be, clear about it, if we were to take that same starting material but look at the trans stereoisomer, we would predict no reaction with HiO4. Okay, so if they're trans, we get no reaction. And then linear alkanes, again, it doesn't matter if they are, what their orientation is because we can just freely rotate. So to look at one example of a non-cyclic system. Okay, so we could just rotate around this bond to make them syn. I'm actually not going to do that because we're not generating, like an alkene to consider E or Z geometry. I just wanted to point out through example, why we don't care about that necessarily with our linear alkanes. Okay, so let's do this reaction with HiO4. Let's go ahead and count our carbons so that we can think about what our products are going to be. Okay, so we're going to break the bond between carbon 3 and 4. Okay, so what functional group do you expect to be at carbon 3 in the products? So as I'm looking at it, since it's a tertiary alcohol, we would expect, and there's no hydrogen bound there, we would expect that to be a ketone. And then carbon 4, as it's a secondary alcohol, we would expect that to be an aldehyde. Okay, so when we have our products, we're going to have our 3-carbon aldehyde plus our 4-carbon ketone. And those will be the products of our reaction. So we've cleaved and oxidized at carbon 3, and then we have carbon 4 oxidized as the aldehyde. Okay, so that actually ends up being the last reaction that is in chapter 10. There's some other ones that you might see throughout the text, but we're skipping those. And so this is where our exam 4 material will stop. I'm going to end this recording, and the second part, anytime I have remaining, I'm not sure exactly where we are in terms of time, but I'm going to come up with some synthesis problems, and I'm just going to work through those, so you can start to get an idea of how to apply some of the reactions from the last few chapters in terms of synthesis.